Motors that are used in handheld tools have to fulfill some basic requirements. They should be lightweight but powerful. Depending on the task, either running at high speed or producing a high torque is important. Powered by batteries, they should exhibit low losses. In this video we show what to consider in particular when selecting motors for application where high temperatures should be avoided, as in handheld tools. The focus is on two aspects: a suitable motor sizing and a matching powering by the controller. How hot can motors get during operation? The answer is hidden in the operating range diagram, just the one you see here. It's of a high-speed motor that could be used in a handheld medical grinder. In red we have the continuous operating range expanding up to the nominal torque. Nominal torque is to be understood as a maximum continuous torque, resulting from the maximum permissible continuous current, the nominal current. The power losses at this current value result in the maximum permissible winding temperature in continuous operation. The white area stands for the short-term operation. It's possible to overload the motor for a short period of time, which means running at a higher torque. The rose area denotes continuous operation with improved heat dissipation. In a handheld tool this is rather not the case, because the motor is encapsulated in the tool housing. The border of the continuous operating range decreases at higher speeds. There is additional heating due to iron losses, and motors can become hot simply by running at high speeds. Accordingly, less current is permitted to create torque. The amount of heating depends on the load. The losses increase with the square of the current. Real high temperatures are only reached in continuous operation close to the nominal current. Motor operation at about half the nominal current results only in a moderate temperature increase of about 25 degrees C. For a handheld tool, this might already be an upper limit. All this leads us to the first rule for motor sizing: dimension the motor too large. Of course, this is not very attractive concerning size and weight. However, what might help is that handheld tools are seldom operated continuously. This table is an example of a test operation cycle for a medical handheld tool, or graphically, the load torque in a function of time. A short analysis. Phase 2 with the highest torque and the longest duration will be the most critical from a thermal point of view. A full cycle takes almost 3 minutes, however more than 1 minute of it is just well. The cycle is to be repeated 10 times. The full test takes almost half an hour. This can be considered as continuous operation. In this diagram we have sketched the operation points on top of the operating range diagram of the motor. The points of operation lie in the left half of the continuous operating range, with the exception of the highest and longest load. What will be the motor temperature if this cycle is repeated 10 times? Let us consider this as a continuous operation with an effective or RMS load torque. This average torque is about 16 millinewton-meter, or about 40% of the motor's nominal torque. This average load of about 40% heats the motor up by about 10 to 15 degrees at the housing. Hence we can expect temperatures close to 40 degrees C, which are still bearable for our hands. There is still the open question: how hot will the motor get during the long 60 seconds load at 25 millinewton-meter? That's about 60% of the nominal torque. This question is related to: how long does it take for the motor to heat up? Assuming a constant load, the winding and the motor temperature follow an exponential curve up to a maximum value. The thermal time constants can be interpreted as the reaction time of the temperature, and there lies the answer to our question. The thermal time constant of our motor is about 500 seconds or 9 minutes, and operation for just 60 seconds will only have a minor effect on the housing temperature. Even more so since the maximum temperature increase is only about 25 degrees, which means we are at the very left end of the curve. Additional note: windings have a much lower mass and accordingly heat up much faster. This has to be taken into account in overload situation. The winding may be burned before you will see it at the housing. Up to this point, the main topic were the joule power losses in the winding. A second origin of losses to consider are the iron losses, in particular the eddy current losses. Eddy currents are generated in all the metallic structures in the motor by alternating magnetic fields. Eddy currents increase with the square of field amplitude and frequency. On one hand, alternating fields are created by normal motor operation, for instance by the rotating permanent magnet and the alternative powering of the winding segments. The faster the motor rotates and the higher the number of magnetic poles, the larger the losses. These effects are taken care of by the curved limit of the continuous operating range. On another hand, high-frequency fields can be induced by the PWM power stage of the controller. Measurements show that unsuitable drivers can increase motor temperature massively. Hence, let us have a closer look. With PWM, the current will follow the pulsed voltage at least to some extent. The maximum current ripple, and hence the amplitude of the magnetic field and therefore the induced losses, can be estimated with this formula. The amplitude of the current ripple can be influenced by reducing the supply voltage. The maximum current reaction will be smaller. By allowing less time for the current reaction, this means increasing the PWM frequency. Or by increasing the electrical time constant. This is done by adding inductance. This formula represents the worst case when the required voltage is just half the supply voltage. It means at 50% PWM duty cycle. The ripple can be minimized by reducing the voltage, which is equivalent to increasing the PWM duty cycle. How important are these additional losses that stem from pulse width modulation? Here some results from measurements and simulation. The speed, 35,000 RPM, is not extremely high, but the worst case PWM duty cycle of 50% was chosen. From left to right you can find the results for the same motor but with increasing additional inductance. At the far right, a power stage without PWM was chosen. The motor heats up just slightly to about 44 degrees C. With the pulsed power stage, there are additional losses, even when a huge additional inductance of 100 microhenry is used, and the temperature is about 10 degrees higher. The smaller the inductance, the larger the current ripple, the more important the losses induced by the pulsed power stage, and the higher the motor temperature. With the lowest inductance, you get a large current ripple and, correspondingly, a nicely hot motor. As a summary, observe these three basic rules to avoid too hot a motor. A motor with a large nominal torque will not heat up as much. Motor housing temperatures react only slowly, hence it's no problem to overload the motor for a few seconds. Some motor designs are specially made for high speeds, but still, keep the speed as low as possible. And third, the power stage of the controller can destroy all these measures. Keep the current ripple small. There is a reason why Maxon controllers have large built-in inductances and operate at high PWM frequencies. That's it in the core. Good luck for your application.